Hello, everybody. Thank you for being here. And thanks to the organizers for this opportunity to report some results of an ongoing project. It's not finished yet. Today we already have several interesting talks on protoplanetary disks. And now what I want to talk about is an object in its later stage of life, that is a debris disk. So after the primordial gas and dust components in the protoplanetary disk has dissipated, we will end up with a system with just a star and the planets orbiting them, and some smaller bodies like asteroids and comets. And when these smaller solid bodies collide with each other, it releases secondary dust, which will emit mostly in infrared, and we call this debris disk. So, for example, this is a debris rain. So we call it debris disk, but it does not really have a full disk structure extending from inner region to 100 AU. It's more like just narrow rings. So in recent years, people start to discover a new category of debris disk, which we call extreme debris disk. They are understood as secondary dust created at very close to a star, within 1 AU to a star. And because they are so close to a star, they are generally warmer and having higher fractional luminosity, and their evolution timescale are very short. So these disks give us an opportunity to study dust evolution within human timescale. So this is one of the famous extreme debris disks. So this photometric data shows that within a time of only 1 or 2 years, it faded dramatically, which means it once had a debris rain, but then this rain quickly dissipated. This is another extreme debris disk, which shows complicated variability patterns in several years with fading and brightening. So theoretically, this could be understood as a result of asteroid collision. So the immediate result of a collision would be a dust clump, that is a huge amount of small dust grains created in the destructive collision between larger bodies. But then when these dust grains orbit around the star, due to their velocity dispersion, this clump would gradually spread out azimuthally so that it finally evolves into a ring structure. So now let's go to our target, which is called HD 166191. So if we look at its SED, the SED could be fitted with just 2 black bodies, one warm component with roughly 700 Kelvin and one colder component with 170 Kelvin. So this could be understood that it just have 2 debris rings. But even though there's also debates that, okay, it could still be transitional disk. So a new progress in the understanding of this object is that a brightening was found in 2019. So within a time of 1 year, the infrared access almost doubled. And also 2 dipping events was found in both optical light curves and in infrared. So this could be explained as an asteroid collision created a dust clump, which happens to be on a highly inclined orbit, so that this clump could create transit events, and this time interval between these two events might be the orbital period of the clamp. Therefore, from this time interval, one could even derive the orbital radius of the clamp. And then the spreading out of the clamp could cause the infrared brightening. Okay, so if this is true, then we have a quickly evolving asymmetric warm dust inside 1 AU, and the angular size would be several milliarcsecond, or within 10 milliarcsecond. Therefore, that would be a great target for a VLTI observation. So we observed this object twice in two epochs, in 2019 and 2021, in L and M bands with Matisse. So here we are showing the visibilities and the closure phase signal. So the low visibility, even in the shortest baseline of only centimeter, means that the object is well resolved. Therefore, its dust component, or maybe most of its infrared emission, need to come from a region at 10 milliarcsecond from the star, or even further away. And the closure phase signal tells us that that the dust distribution is asymmetric. But this is changing because in our first observation, the closure phase signal is quite strong, but it gets weaker in the second observation. So this kind of asymmetric distribution and temporal variability seems to be a natural result of dust evolution after an collision event. So here I show the results of our modeling. So our model setup, this is my, well, it's kind of simplified. We have a star whose flux is already known with SED fading. We have an inclined ring, and we put a clamp component, which we assume would be represent the newly created star. Newly created dust, and it can be off center, which it means, yeah. So this is the best fit parameter. I will not read it, but the general information is that with this kind, with this kind of ring and clamp structure, we can roughly fit the results, and we find the ring need to be highly inclined. But since the fractional flux of clamp is much smaller than what we expected for the newly created dust from the photometric observation. And now we think maybe this point source representation of the new dust is too simplified, and we should, in next step, we would try a more sophisticated model that is an azimuthally modulated ring, that is a ring structure, but being brighter on one side than the other side. Another interesting result is we find that the dust needs to be roughly 1 AU away from the star. So that is a larger distance than estimated before, which means the orbital period cannot be so short. Therefore, that two dipping events could not be one clamp passing through the line of sight twice. It must be some other reason. Okay, so thank you.
Okay, thank you very much for that lovely talk. Does anyone have any questions, either online or in person? I did have one quick one to get started. How many of these extreme debris disk environments are there, and how many are accessible with VLTI or Chara?
I think there is only several objects available for this because the object need to be bright enough, and also the angular size need to be large enough. Several colleagues, including Joseph Varga and Attila Moore, are working on another project, which is a small sample study of several debris disks. I think that includes all the extreme debris disks which could be accessible to VLTI, except this one.
We have one question online as well. So have you thought of looking for gas from these collisions with ALMA, from Evan?
With ALMA, I think that could be, I mean, there would be too little amount of gas. It could not be detectable with ALMA, I think.
Okay. Could it be detected with anything else, or is it?
I think not with current instruments, I guess.
Thank you. Is there any other questions?
Yeah. Hi. On the SED you showed, and also the estimate of the temperature of the clump, it seemed as though it was warm enough that you might be able to get some K-band emission from it. Has anybody thought, tried near-infrared observations?
It's a little too cold for K-band. If we see the that plot, yeah, so in K-band it's almost 0. Yeah, I mean here, right? At 2 micron, we basically get nothing, no excess.
Any other questions? Oh, one from Stefan. Oh.
Yes, hello. Nice talk. You mentioned some paper from Melis 2012 with this TYC82 object as an example for such an extreme debris disk. And I remember that they made really didn't have a plausible scenario at the time what causes this rapid disappearance of the dust in the 2012 paper.
Yes.
So do you think this is now resolved and we can really explain what happened there?
As far as I see, there's no explanation for that yet.
Okay, but we have no more objects that are as mysterious as TYC82.
Yeah, a lot of it, well, mostly extreme debris disks show a quite dramatic variability, but this kind of completely disappearing of the debris ring, I think this is the only one.
Okay, it's the most extreme one in that sense. Okay, thank you.
Okay, if there's no more questions, we'll move on. If we can thank you again for a nice talk. So up next, I believe we have Julia Kobus, who's joining us online.